So purine biosynthesis will take us at first 11 steps to get to IMP. And then from there, an additional 2 steps to either AMP or GMP. It's quite complex, so I'm not going to ask you to memorize the steps or anything like that. There are multiple rate determining steps within this pathway. Step 1, step 2, and then after that branch point, additional regulatory steps towards AMP or GMP. Also kind of cool note that some of the enzymes in this pathway are actually involved in protein complexes. Think back to when we learned about the pyruvate dehydrogenase complex, and it was a massive complex with multiple enzymes in it. That's also true for other pathways, such as this. So enzymes 3, 4, and 6, for example, all in one big protein complex. 7 and 8, and 10 and 11, also true. And so how this helps us is that we can kind of shuttle those substrates and products from one enzyme directly to the next. So it doesn't leave the protein complex, it doesn't go to some side reactions we don't want to happen. We can just go bam, 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 kind of all of these reactions in a row more quickly and efficiently. Let's jump into it, folks. On the slides, you're going to see that I keep this picture kind of at the top because I'll be mentioning when we add this nitrogen or this carbon. So here is like the backbone of our purines, and we're going to watch it built atom by atom. Let's start with the first 3 steps. Step 1 is performed by ribose phosphate pyrophosphokinase. Okay, so we're starting here with our first metabolite, R5P. And what we're going to do is activate this molecule by hydrolyzing a high energy bond, ATP. And we're going to add on those 2 phosphates, that pyrophosphate. So we're adding on this part here. And this intermediate, this metabolite PRPP, is used in a variety of other synthetic pathways, such as synthesis of pyrimidines, histidine, and tryptophan. Moving on to step 2, performed by amidophosphorybosyl transferase. Should have slowed down when I was saying that. Amidophosphorybosyl transferase. Well, this is going to be the main flux controlling step of the pathway. While step 1 is also a rate determining step, step 2 is really targeted for flux of the pathway. Here, what we're doing is we're adding the amino group N9, so this one here. And we're doing that by using glutamine. And so we're grabbing the amino group, from glutamine and popping it on to the ribose ring. At this point, folks, we've also set the anomeric form of the nucleotide to be the beta form, which all nucleotides will follow on with. Then step 3, performed by GAR synthase. Here we're adding in a few different atoms, so 3 atoms more than all the other steps, that's just kind of one at a time, by using glycine. So we add in that glycine and we'll get C4, C5, and N7. So that is C4, C5, and N7 in this step. Right there. Now what about the next 3 steps? Okay, so step 4, performed by GAR transformylase. We're going to take GAR and we'll add a formal group that is a 1 carbon transfer to add the C8, this carbon here. And we're popping it on to the free amino end So bam, we added that one carbon unit right onto the end of that amino group that was hanging off. Next up, FGAM synthase. We're going to add another amino group, okay? We're adding it again from glutamine to give us the N3. So now you can see that glutamine has added two of our amino groups here. And we added that right there. Then step 6, performed by AIR synthase. This is an intramolecular condensation and tautomerization. So you can see here that we're going from this open structure, and we've done an intramolecular condensation to close the ring. We also have a tautomerization to convert this structure into one that is then aromatic. What about the next 3 steps, folks? Remember, let's not focus on the details here. We're just getting an overview of the pathway to understand it. Step 7, performed by AIR carboxylase. We're adding the carbon 6, not via a 1-carbon transfer like we saw previously with a formal group, but actually through bicarbonate. So that is C6 up here. That is being added, and on the structure, there it is. Next up, step 8, synthetase, excuse me. Here we're adding another amino group. The amine is now coming actually from aspartate. So here is that N1 amino group from aspartate. And yes, while in the end we're only just going to need that amino group, you can see that initially this enzyme is adding the amino acid, aspartate, to the structure. Step 9, adenylosuccinate lyase. Here we're going to eliminate fumarate so that we are only left with that amino group left on the structure. Now in this kind of amide functional group, chopping off fumarate and all the rest of those atoms because we do not need them to move on. We're almost done, folks. Step 10, performed by AirCard transformylase. Oh, I have one too many R's. I'll fix that before I post this. ICAR transformylase. Here we are again adding a formal group, a 1-carbon transfer. That's going to give us the C2. Okay, so you can see we used a formal transfer for 2 different carbons to make this structure. And here it is. Last step before we get to the primary intermediate, IMP, inosine monophosphate. Here we have IMP cyclohydrolase, right? We know that these purines have this 2-ring structure. We closed the first ring, time to close the second ring with again an intramolecular condensation and cyclization. And we have this nice two-ring structure here at the end. So this is the first 11 steps, but we're not done because we actually have to get to the nucleotides, AMP and GMP. So just 2 more steps either way, folks. To get to AMP, let's look at the left side of this picture here. First, we have adenylosuccinate synthetase adding aspartate to replace this, let's see, I'll draw the arrow from here, to replace the 6-keto with instead what's going to be just the amino group. Following that step, where we've added the entire aspartate on there, we have adenylosuccinate lyase, which is actually from step 9, folks, cleaving off, again, fumarate. Let me go back 2 slides here. You'll see the exact same chemistry is being performed, right? We're chopping off that fumarate after having added the aspartate. And that leaves us with this amino group here. We have made AMP. Now for GMP, we have some different steps happening here. First, we have IMP dehydrogenase oxidizing the ring. So we're going to oxidize right here at this carbon by adding this ketone group. And then to get to GMP, we're going to replace this ketone with an amine, again from glutamine, to finally end at GMP. That was a lot of steps. And on this slide, you can see how complicated it is because I'm showing you all the steps at once. What are some things that we saw kind of as patterns here? We saw lots of ATP being used in these steps. We have to remember that now we're looking at an anabolic process. When we're building these biomolecules, we usually have to use energy in the process, right? This is going to cost us energy. We also use GTP. We saw glutamine being used, glycine being used, and aspartate being used to make these structures. We also saw the cofactor THF being used to do that one carbon transfer with the formal group, and bicarbonate. To wrap up the next video, folks, and the section on purine synthesis, we'll talk about regulation.